In this video, we're going to be completing a one-sample t-test. So there's going to be a lot of similarity with the z-test that we've already seen. The difference here is that we're now going to be working with means where we don't know the true standard deviation of the population that we're working with. So when we worked with proportions and we had a null hypothesized proportion, what we could do is use that null hypothesized proportion to calculate what the standard deviation should be under that null hypothesis, because calculating variation with proportions is just very different. It's a lot simpler. Whereas with means, we really can't know the true standard deviation of a population from just our sample. Even with the null hypothesized mean, that isn't going to tell us the variation in the sample. It's a little bit different now. So instead what we use is the sample standard deviation. So how much variation we see in our sample to kind of approximate that value and use it to approximate the standard error of x bar. So when we do that, we recognize there's going to be some error in our process. So what's going on now is that x bar minus the true mean divided by the true standard error for x bar follows a normal distribution. This is still true. X bar follows a normal distribution centered at mu, and I could say that x bar minus mu divided by the true standard error is going to follow a normal distribution with mean 0 and standard deviation 1. It follows the standard normal curve. So I could use z-scores in that case. However, if I'm approximating this value, that changes things a little bit. This is now going to be prone to have slightly larger values than I would typically. And so even though we don't spend a whole lot of time kind of breaking this down, if I add that approximation in the denominator, this is now going to follow what's called a t-distribution, which is also centered at 0, but has slightly what we call fatter tails, meaning that I might get t-values that are a little bit farther away more often than I would with a normal distribution working with z values. So again, we're not really digging in a whole lot into the t-distribution more than we just need it and use it. Just remember that the t-distribution is like an approximated normal distribution that we use when the variance is unknown in this population and we have to approximate it. That's really all you need to know in this class and to be successful using these methods in general. All right, so because of the approximation error, I need the t-distribution, which is an approximated normal distribution that accounts for that error. All right, a further word about directional hypothesis test. Man, I feel like I've already talked about this, but let me just kind of check these again. I don't think there's anything super important here. Honestly, I think you can kind of read this on your own, other than just this notational thing, that we are going to be using some directional notation moving forward. So as an example, let's say that we're studying whether or not smokers have a higher systolic blood pressure reading than the general average of 126. And let's say that we only find this result interesting if smokers are higher than 126. We're not just asking if they're different. We only care, and we're only going to do something about it if smokers have a higher than average systolic blood pressure. So in this case, our alternative is going to be that mu is greater than 126. This is a direction in which we are interested in. This is the researcher's hypothesis. It's the thing that means a change of note for us. The null hypothesis, we could write it as mu equals 126, but more commonly when we're working with directional testing, we actually want to make the null mirror the alternative here. So if our question is, do smokers have a higher blood pressure than the general population, we're going to set our alternative in that direction with mu being greater than 126, in contrast to the null, which is now going to mirror that and say that mu is actually less than or equal to 126. Notice here the null hypothesis always has that equals component, right? So that equals component accompanies the null here. The alternative does not have an equals component. The alternative has to either be not equals, or it has to be only a greater than or a less than sign. So just keep that in mind. So a low p-value is going to signal that this benchmark is a bad assumption for truth. Higher p-values signal that the benchmark is reasonable, not necessarily true, but reasonable. That's still kind of staying the same. But just kind of be aware of this notation moving forward, that we're going to be using it in a practice problem coming up. All right, so child psychologists recommend that children under age of 6 have no more than 1 hour of screen time a day. A researcher studying whether children under 6 are watching more than an hour of screen time or not. She takes a random sample of 45 children in a particular community. She finds that the average amount of screen time in her sample was 1.27 hours, with a standard deviation of 0.56. All right, so number one, what is the null and alternative hypothesis here? So let's kind of take note of the population. It is, we're sampling from a particular community, so we should probably kind of reflect that in our statements here. So we're not necessarily generalizing to all children, but children from the community who she is sampling from. The null hypothesis would be this benchmark comparison, that there's nothing going on here. So it would be this idea that they are getting an hour of screen time or less. The alternative, I think, is the more obvious thing to write, and that is that they are getting more than an hour of screen time. That mu is actually greater than 1. Children in this community are watching, I don't know if watching is the right word, are getting more than 1 hour of screen time on average. And notice here that I'm saying on average at the end. I'm referencing the parameter that we're talking about, and that's important here. So I'm not going to just say that children in this community are watching more than 1 hour of screen time, because I'm sure that there is individual children who are. The question is whether the mean is greater than 1 in this community, that on average screen time is more than 1 hour. So make sure that you do clarify what parameter we are measuring. Otherwise, it just kind of sounds like, do individuals exist who are getting more than 1 hour here? The null hypothesis then is going to mirror that, right? So we're going to say it's less than or equal to 1. And notice here, this makes a lot of sense as a directional test, because it's not that it's important that they're getting exactly 1. It's just important that they're getting no more than 1. So that makes sense as the null, that they're in that okay range of less than or equal to up to 1. And the alternative is going to be that that value is greater than 1. And we're going to use 1 as our benchmark when we test this. So we're going to say, well, let's assume it's 1, and let's look at the sample we got, and let's see how unusual it is in comparison to this null that it's 1. So then we're going to say that children in this community, blah, 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 are getting 1 or less hours of screen time. Or I guess I could say no more than 1 hour of screen time would probably be the less awkward way to say that, but same idea. They're getting no more than 1 hour of screen time on average. Oops, I almost forgot that after making a big deal about it. All right. What is the standard error for our sample mean? So it's going to be, again, the same formula that we've seen before. It should be sigma over the square root of n. We don't know sigma though, right? So again, we're working with means. We just have our sample data. We're not going to know what sigma is usually when this is going on. Instead, what we're going to do is approximate it with our sample standard deviation, and we're going to kind of estimate what that standard error should be. So S is going to be apparently 0.56. Right, so if I kind of go up here, our sample has a mean of 1.27 with a standard deviation of 0.56, so that is how much variation we see in our sample with screen time. We also have 45 children, so if it kind of helps to write this information down over here, so n equals 45, S equals 0.56, X bar equals 1.27, so there we go. Now, I'm going to calculate this out, and I'm going to get 0.56 divided by the square root of 45, and I get 0.08348, so I'm going to do 0.0835. I'll go to 4 decimal places there, 0.0835, just because I feel like it. Okay. How many standard errors is our sample mean away from the null hypothesized mean? In other words, what is our test statistic here? So since we're using an approximated standard error, this is going to be a t-value. It's not going to be a z-value because we don't have the true standard error. So we're going to have a little bit of error correction that we note and use a t-distribution with. So this is going to be x bar minus our null hypothesized mean over our approximated standard error for x bar. So that's going to be 1.27 minus 1. So we're going to use 1 as our benchmark. We're going to assume it's up to the maximum and run with that. So if it's 1, how unusual is this? And this is going to be 0.0835 is our standard error. So if I calculate this, I'm going to get 0.27 divided by this standard error value, and I get 3.234. So I am 3.234 standard errors above what I would expect to get if it was really 1. So that's a pretty big distance. And using R, we can use what's called the PT function, which isn't super important for our class, but we could use R to do this, and we get a p-value of 0.0012. So let's shade the curve and think about what conclusion makes sense here. So we are way over here. We are like, so if this is 0, if this is our t-distribution, so let's say this is our t-distribution. Actually, you know what I'm going to do? I'm going to do the t-values below it. And I'm going to say this is our distribution of possible x bars. Oops. So this is 1. This is about 1.0, or well, it would be a little bit farther, honestly. So let me do this. This is about 1.08. This is about 1.1617 in that 2 standard error range. This is about close to where we are, so about 1.25, and we're way over here. We're at 1.27, so we're like right here. And this is our shaded region. This is our p-value. Our t scale I can kind of put under here. This is 0. This is 1. This is 2. Oh, you can't really see that there. Let me do that again. 0, 1, 2, 3. So we're a little bit more than 3 estimated standard errors off. So that's why our p-value is so low. Our p-value is well below 1. Or I should say it's well below 1%. So this right here is 0.12%, by the way. So if I move that decimal place over 2 places, that's a percent now, 0.12%. So we have very strong evidence. Oops. Against the null hypothesis. I'll just write H0 there. Right, so if the true mean really is 1, think about how unusual this result is. That if I take 45 children and get a mean of 1.27, maybe individuals in that range makes sense, but to get 45 children averaging at 1.27, it seems pretty improbable now that the true mean in this community would be 1 if I appropriately sampled from this community. So that's why my p-value is so low, just suggesting that this is not something that I would commonly see by random chance if it was 1. Again, it's not impossible, but this is about a 1 in 1,000 result. It's almost a 1 in 1,000 likelihood, apparently. So that's why we have very strong evidence against the null hypothesis here.